Okay. Hi everyone. I'm Ali. I'm a 2015 Tron grad. I just joined Apple about a year ago, and I'm gonna start off with a talk on 3D printers. So first of all, who's familiar with them? Okay, that's quite a fair bit of you. I was expecting a lot less experience with them, so I kind of really toned down the talk. But feel free to ask questions or jump in with your input at any time. As I'm going through, if you have any questions, just stop me there and take your question and we'll kind of continue on. So, 3D printing. For those who don't know, what's the big deal? First of all, if you ever see this printer in a store and someone ever tells you to buy it, do not buy it. It's actually the worst value for money, and it's a really shitty printer for what you pay for it. So what it is it's the process of making physical objects by adding material to a surface in the most fundamental sense. That's additive manufacturing. For those of you that are familiar with it, it's separate from traditional manufacturing techniques, which is subtractive. So when you have a big piece of metal, you CNC it and you take away the material. Additive manufacturing is you just add material together. And there's two major ways of doing it. And one is FDM, which is fused deposition modeling, and the second one is stereolithography, for SLA. So what are those two? So the first one is FDM, and it was actually invented in the 80s by this guy called Scott Crump. And it's a really simple concept. If you look at it now, you've got a heated nozzle that is putting material down onto a bed, layer by layer, and that kind of sits on a moving table that determines where that material is going to go. Now, the reason why all this stuff is so recent is because he patented the shit out of this. And he founded a company called Stratasys, which has been selling expensive, ginormous 3D printers for the past 20 years. And you can find those in expensive orthopedic clinics or big companies that do a lot of manufacturing and do a lot of prototyping. The second technique is called SLA, stereolithography, was also invented in the 80s by this guy called Charles Hull. And this one is a little bit more complicated. What it involves is that you have a giant layer of liquid polymer. And the idea is that you shine a laser to specific positions on your liquid, and as you're doing it, you kind of move this platform down. And again, you do that layer by layer, and at the end of it, comes out a physical part. So, guess what? This was also patented, and there was another major company called 3D Systems that was founded based on this concept, and those patents also recently expired. Now, what's interesting is that this one we don't see as much because liquid polymers are hard to deal with, they're expensive, it's a pain in the ass to try to do it yourself. Okay, so I'm just going to go over, why is this? Okay, good. Yeah, so I'm just going to go over how the concept of it really works. You've got something like that, a ring, which is like a 3D model. And what you put it through is this program called Slicer, which is a G-code generator. And what that does is basically it takes this three-dimensional model and turns it into these tons of 2D layers. And for example, layer 1 could be just like the base of the ring. And layer 45 could involve something like that, which is kind of showing the head of the dire wolf. And then all this is packaged into this thing of whatever how many layers, 500, 600 layers, and it goes into G-code. Now what's G-code? So G-code is basically this programming language that was developed at MIT in the 50s. And it's used to control automated machines. It's been used for 50, 60 years. And what it does is that it tells any tool. Now in FDM, that's the extrusion part where the material comes out from, and an SLA would be where the laser is, what coordinates to move to or point to, how fast to do it, and what path to take to doing that. And all those instructions are basically packaged into this set of G-code. And that's basically what's telling you, that's basically converts all your instructions of what your model is into a set of 2D instructions on where to go, how fast to go, for the actual printer. And this is used in CNCs, it's in automation. Basically, any machine that we use today to build stuff uses G-code. And this is not working.
You just press it on the...
Okay, so basically once that happens, your computer gets those instructions in G code, it goes in layer by layer, and your part comes out.
It doesn't work when you just press on it.
Okay, so the next thing is like, okay, so this is a basic concept of printers, but there's a fuck ton of printers everywhere on the market. You're gonna have small ones, large ones, big ones, and one of the questions that a lot of people want to get into 3D printing is like, which one should I go for? What do I want? What am I looking for? So the basic thing is what kind of a printer do you want? Like, are you like a tinker? Do you want to kind of get one to like make yourself, or do you just kind of want to get something to plug and play and go just start printing stuff either off the internet or stuff that you've designed? Another thing that's important is FDM accuracy is about 0.1 to 0.05. So what I mean by accuracy is the layer height. So basically how thick that layer is when you break down your 3D model into these 2D segments. And FDM goes down to like 0.1 to like 50 microns. And stereolithography is really great, and it can go down up to 5 microns. But then again, you have that problem where you're dealing with expensive material and handling and maintaining a laser and all those things. Material needs are also things, I don't know if you guys are familiar with any of these materials. ABS is a slightly harder, better plastic, but the problem with that is that it requires more heat, requires your extruder to be a lot harder, and it also requires your heat bed on your printer to be a lot harder to work with. What you get with is plastic that's more rigid and will last longer, and is better than PLA, which is like your most common material that people like to 3D print with. Then you have silicone, flex, nylon, lots of different kinds of materials. And then you have your print size. Are you trying to print jewelry? Because then you really need a really small print bed. If you're trying to need something fairly large, they can go up to 20 by 20 centimeters. And then you can have these weird sizes where you have a circle with this diameter and it's half a meter wide. You can basically go to town with it. The next thing is cost. And this is just a general estimate of if you're trying to get a printer, this is how much you can kind of expect to spend. So this is that weird printer where you have this thing and then you have this really long tall thing for something that you might want to print. But if you're going to spend $100, $500, you're going to get a printer that you basically have to assemble yourself. And it's probably going to be either that or a really small, tiny print bed that's going to be a plug-and-play printer that you can get. 500 to 1,000, I consider this the sweet spot because you can get a decent big inner printer, or you can get a really nice build-it-yourself printer. And that's kind of the range that I picked from, so I can tell you about my experience with that. 1,000 to 2,000, those are your nice, fully featured plug-and-play printers. They're really commonly used in a lot of places, including companies. We actually use printers at that level just to do our own prototyping for mechanical stuff. And then $2,000 is the big leagues. You're gonna get your fancy printers that will make flex materials and silicone and rubber. Don't get any ideas, but anything that you can kind of think of. Yeah, so basically what did I pick? So I spent a shit ton of time doing research and I kind of went with this really simple one. The reason why I specifically mentioned from Prusa Research, because there's a lot of versions of the i3 Prusa printer itself out there. And you can go on Amazon, you can get one for $250 and it'll ship from China and you'll get no support and your parts will come up broken and it's gonna suck. Or you can kind of go mid-level with some different levels of difficulty. Or you can kind of go with the best possible one, which is the guy who actually designed this printer. He runs this research company in Europe, and he mails out these entire kits. Now, what's weird about this kit is it's kind of like an open source community project. The entire build of material, so everything you need to know to put this together is actually out online, and you can source the parts individually yourself and put it together if you really want to. And the cool thing is that all these little parts that you see over here, these are actually 3D printed. So you can use a 3D printer to print a 3D printer, which is great, right? So this is really good because then you can, the first thing I do when I assemble this is I just print a set of spare parts just in case shit breaks. And you can use this to kind of upgrade your printer as you go along. This was a really good deal because I got a pretty big print bed, and there's tons of material options with this one. And there's a great community of people that are like working and they've done their own mods and made cool improvements on like making it better. Like someone did like instead of having one extruder, they were like, okay, we're gonna have 2 extruders so they can print with 2 colors, and they kind of just did it on their own. So I got this heap of junk in the mail. As I said, you'll get a ton of them in different qualities, and I've got lots of horror stories of like some of them ended up being complete shit when you put together. So you kind of want to be careful with where you go and make sure you do your research. What I got was great. All the parts were labeled, everything was assembled, it was great instructions. It was like pretty straightforward. There were some hiccups. This thing is like put together by zip ties. Like literally half the stuff you hold together with zip ties. So I ended up breaking a ton and they were a lot really loose. All that shit. Some plastic parts came in broken. I kind of lived with it, or I just downloaded the CAD and had it printed somewhere. And then this one was kind of like really annoying because I had to take a few trips to Home Depot and find a way to get this screw to work with this. So all in all, it took about say 40 hours of like build time. So like over 2 weekends, I put this thing together and I got it working pretty well. And yeah, so I actually have some samples of like what I printed out with it, and they're pretty good. So you can just pass these around. Yeah, so it actually ended up. It took a little while for me to like move this around to like get it loose, but they came out really well. The frog itself, like I printed at like 50 microns, so you can. It's pretty detailed on the top, and you guys can see that it was actually. I was pretty happy with it because I invested like $600 and I got a pretty sweet quality printer. Now, I kind of want to talk about like what's printing actually used for today. And there's kind of 2 major things. Right now, in the past few years, ever since like those patents expired, it's become a big thing in rapid prototyping. So every time you want to try shit, you just, make it, put it in a 3D printer, see what works, see what doesn't, and then iterate from there. And the second thing that's taking off in is doing a lot of customized work. So that's a lot of things involve like the human body, right? So you have this cast that was 3D printing to the size and fit of a particular person. So we're seeing a lot of applications of these in orthodontics, orthopedics, all those kinds of things that involve like bones, restructuring teeth, all those things that are individual. Now, a lot of people are like thinking, hey, this is going to replace mass manufacturing. We're not going to buy stuff. And as someone that like works in manufacturing, I strongly feel that this is not the case. Fundamentally, because like as you start scaling up, trying to scale up 3D printing, the cost just goes up exponentially. And it's faster, cheaper, and almost always better, unless you're like having a customized thing for every person, to just use it like using injection molding or like a ton of other techniques that people use to do it. So I personally say this is not going to be used for mass manufacturing. Well, then what is it going to be used for? Well, one funny thing that's going to come out of it is like basically anything that can be extruded is going to be extruded. There's a guy that made a chocolate 3D printer. Uses the same concept, and you can make like cool chocolate. Another person did like a pancake printer, and like he's gonna extrude pancakes. This like that's gonna happen. I don't think that's the main application, but I think it's a great thing. This little thing is really cool. What this is a little company out of Queen's University built this thing called Palette, and what you can do is you can feed in 4 or 5 different kinds of 3D filaments, and then what it does is that you can code it in so that it'll split the filaments out and rejoin them, so you can get different colors, and that allows you to do like 3D color printing. I think these are on pre-order for like $600, but it's a really cool thing that they managed to do this thing where in real time you can melt a bunch of plastic off, put it together, and then keep feeding that through. And the next thing is what I think is something to be excited about. So Volterra, I think a lot of you guys know about Volterra. They're making like 4-layer circuit boards. what I want to show you guys a video on. Do you have sound?
Turn it up on the.
I'll make sound effects.
Okay, so
if you could 3D print electronics.
At Voxel 8, we're revolutionizing 3D printing by developing a full three-dimensional electronics printing platform.
So if you take a look at a lot of what's been printed up until now, it really amounts to trinkets in 3D printers. And as we look to the future, that's where I think we're going to start creating things that only 3D printers could have made.
The circuits of today are flat two-dimensional circuit boards that are embedded into three-dimensional cases. Now, this whole paradigm is going to change because we're enabling designers to create circuitry and physical objects at the same time using Voxel 8's 3D printing technology.
Over the past decade, the Lewis Group has carried out thousands of experiments to create new materials for three-dimensional printing. I'm really excited to move this technology out of my lab into Voxel 8.
With our Developers Kit printer, you will be able to integrate electronics into mechanical objects. You will be able to print devices like quadcopters and integrated electromechanical assemblies that typically have to be manufactured through multiple methods. Our conductive ink is specifically formulated for 3D printing. Prints and dries at room temperature, has excellent electrical properties, and has excellent adhesion to other matrix materials.
We want to make it simple for users to create 3D printed parts with embedded functionality. We've partnered with Autodesk to make an end-to-end pipeline to do just that.
Wire enables users to bring in their CAD models, to place components, to route wires in 3D using the Autodesk Spark platform. And that's really happening for the very first time. The software for this simply did not exist before.
We're fundamentally materials experts, so we created a platform specifically designed to be upgraded with different materials as we release them in the future. Our printer prints similar to typical 3D printers, layer by layer. To place a part, the printer stops, allows you to remove the bed, place the part inside of the material, and then replace the bed on the printer. It will print right where it left off, knowing that there's a part inserted inside of it.
We're excited to work with companies like Voxel 8 because they're really pushing the boundaries of where 3D printing is capable. And by incorporating conductive inks directly in the 3D printing process, we can start to create things that have function after they're created.
In order for 3D printing to reach its full potential, we need a broad palette of functional materials, coupled with the ability to have a multi-material 3D printing platform. With these kinds of tools at hand, we can truly print our imagination.
So, the whole thing, look aside. Okay, let's get back to the presentation. Okay, somebody help me out here. Got it. Okay. So, the whole Kickstarter thing aside, this represents a really rudimentary take on what I think is going to be how whole 3D printing thing is going to affect manufacturing. Is we're going to be able to make do a lot better in terms of integrated electronics and take a lot away from that assembly process. So this would have been cool if we did this after the take apart, because then we could kind of look at it in the context of this is how a speaker system is put together, but imagine if the whole speaker was kind of 3D printed as one object. And I think that's where we're going to make advances, not not with something like this, but over the next 5-10 years. That's how I think this is going to affect manufacturing. So just in summary, what 3D printing does is that part complexity is a lot cheaper. And I think that affects at most the assembly of products, physical products. We're going to get better with prototyping. There's going to be a lot more customized products. But what it's really going to enable over time is going to be allowing us to do complex manufacturing and make parts that are just printed by themselves versus a bunch of people putting things together. Thank you.
Do you know anything about how recycling works? Recycling and reusing?
Yeah. You say how they do recycling?
Yeah, for example, when you have the integrated electronics thing, you can't really do maintenance on it.
No, you can't.
Destroy the part.
Mm-hmm.
Unless you buy it anyway.
No, I think that's obviously there, but I think that there's always in terms of taking apart parts, there's always ways of taking apart parts. If you like, I don't know if you've seen like that the Apple robot Liam who like takes apart iPhones. Like yes, you're gonna have to like get a laser to like cut through the plastic, but ultimately, what you should be able to reuse all the materials if you develop a process around it. As far as like physical electronic, like as far as like reusing 3D printed material, I can tell you in terms of like plastics manufacturing, when people like make plastic and molds, they reuse everything. Like they try to reuse like all the shit, all the waste that falls out. So with 3D printed parts, there's actually a lot of potential for them to like, just once the part's wasted, you take all the electronics out, you can take it in and put it back in, molten it up, and print a new filament out of it. So it's actually would help recycling. But yeah.
What happened in the last 30 years that made it suddenly?
So what happened was that the two patents that I mentioned, like 1980s, they expired 2008 and 2007. And like if someone patents such a fundamental part of 3D printing, they own the monopoly on it. So it was only when these patents expired that this whole space exploded. Now, everyone and their brother are like, designing and coming up and making 3D printers.
So where do you see like the next big thing for like what's the next advance in 3D printers right now?
I think like the one thing is like I think integrated electronics is going to be a big deal, and I think that's going to be a bit slow to come because it's going to require significant innovation. I think that's the right direction for it to take. The other thing is that within 3D printing, we're going to see like color printing. We're going to see people doing like cloud-based printing, where people are you're going to go to Staples or you're going to say, oh, you can just click from home, send your file, and you're going to go to Staples and overprint it. So you'll see a lot of those things that we have, but in terms of 3D printing, I think the next set of advances is going to take some time, but it's going to be along the lines of something like complex manufacturing. Any other questions? Yeah.
So what's wrong with this one? You didn't say anything.
Oh, it's this one. So this one is a $3,000 printer, and your print bed is smaller than the size of the printer that I have. And you have to purchase their, I believe you didn't have to before, but for MakerBots you have to purchase their filament. And I personally work with one of the earlier iterations of this one, and it's just, there's a lot of reliability problems, you have to keep messing around with things. So it's like a more expensive printer that prints smaller and has worse reliability than way cheaper printers, which is why I would recommend anyone against it. MakerBot was kind of like the first to the market, so they got a lot of publicity and they made like a lot of printers. But in terms of quality and in comparison to other stuff that's on the market, they're really not all that great for the price.
What kinds of things have you been printing recently?
Huh?
What kinds of things have you been printing recently?
So I'm trying to actually print a drone, but I have been really busy at work, so I haven't had much of a chance. But there's tons of cool stuff out there. There's there's a bunch of CAD for like drones that you can just download and you can get the other parts yourself and like put the thing together. So, yeah.
Is this printed in as one part?
Yes. So that was one of the cool things that I got to print, and the printer came in. This came in like as a preloaded file, and it turns out that if you set spacing in your part in your like CAD file before you print it. You can actually like print moving parts within each other, like at least up to a single layer. So there was just a spacing between those individual gears in the CAD file, and when it got printed, I just let it set for a while, and it came out being able to work. It was really hard when I initially did it, but then I just kind of crunched it up, and now it's really works. Yeah.
Cool. Thank you
All
very
right.
much.
Thank you.
There we go.
And then there's inputs at the bottom for some reason it's a memory card, reset button, box, mute. Okay.
Yeah, I guess also the inspiration of this is basically, we're all working in electronics, and basically when someone comes up with something cool, you buy it and then you take it apart. and you see animated, and then you don't tell me. Yeah. Okay, so we're gonna start trying.
So I guess the first comment is this like blue exterior. So when we would do this, we would talk about the material. So this material is probably a silicone like rubber, and the reason why is it's good for like you can touch it a lot and like
you guys take
it's also good for sealing. Like a lot of times, like O-rings and like sealing features, you'll have silicone as your material, some shore hardness. I don't know how they use that. And also, it can be compression molded. So, compression molding is pretty much this process where they take like a sheet of rubber, they put it in a mold, they heat it up, and they kind of just squish the part together into the shape. So in this case, we take this part, we talk about the material, and then we start thinking about how they actually manufacture it. So I say compression molding, and then we look at it and start thinking about what the tool looks like. So what are we looking for? So we're looking for tooling marks.
But Jeff, what's a tool?
That's a good question. So there's a okay.
There's a bucket.
Where?
Clear basket.
Okay.
Oh, that's the basket.
Probably doesn't know. Okay, so let's say you're making this part, right? There's gonna be a mold, okay? And there's gonna be two halves of the mold. So there's one mold that's gonna fill mold.
I'm just messing with you.
So there's two halves of the mold. And what happens is there's a core and a cavity. So if you can imagine, the core is gonna actually be the internal volume, and the cavity is gonna be the exterior volume. So between the two parts, you'll be able to form this part. So there's actually a slide all the way over there. I don't know where to it. So this is the mold, and this is the part in question. This is injection molding, but these are the two molds, and what I'm talking about is that your part gets formed between these two like steel pieces. Okay? Does that kind of make sense?
Yeah, also having your computer and your screencasting your phone.
Okay. So anyway, so what are we looking for when we look at this piece? We're looking for.
Hey, you guys?
We're looking for things like what the tool is like. So the tool draw direction. So what that means is you have their mold and you're wondering like how they open it. So in this case, this piece is actually probably just this flat rubber piece. They wrap it around like a cylinder, and then there's looks like a piece that comes from here and then a piece that comes from the two sides. So how do we know that? We look at artifacts. So if you zoom in really, 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 really close, it's hard to see. So there's a seam. You guys can see it.
You can see it on the camera.
You can see it on camera.
Oh, you can?
Yeah.
So there's actually a seam running
Well,
along.
it looks better than looking at it with your finger.
It's running along here, you guys can see. So that's how we know exactly where the mold is, because it's pretty much impossible to get like a very. So if you imagine closing two surfaces together, there's always going to be a tiny little gap between, and you end up with these like straight lines. Essentially what we call them. And we also know the draw direction from the features. So if you have a feature that looks like this, obviously you have to be drawing from this direction.
What if you wanted to get rid of the seam lines?
So getting rid of seam lines is Apple's specialty. Yeah. So a lot of people do it. It's like it's specific to this. I don't really know how they do silicone rubber and how they get rid of seam lines. But he's talking about essentially post-processing. So any finishing processes after you molded or whatever your plastic. So they can do things like essentially sandpaper, a very nice sandpaper, and you kind of wipe away that line and you won't really see it. So
How does it have like curve like that? So it started as a flat piece and then
it started as a flat piece, yeah. So they essentially put it in a piece that looked like this.
Yeah.
And then all the other pieces came around and slapped it and then closed it. So that's how they ended up making it.
So I think high level basically this is a $20 speaker bought in China. And then I think with any electronics, you basically try to like factor in cost is a major thing. How do you make it cheap as possible. Yeah, and then so I think these themes will keep reoccurring as we talk about stuff. And then basically how you can make like a lot of them, so like reproducibility, manufacturability, and then there is like feature set. So basically I think that's where like engineering comes in, is that if you have unlimited money and only have to make one, it'd be really easy, it's just really expensive. So yeah, I think everything you'll see. Cool. Okay, so I'm gonna do this part. So this is battery cover. Sure. Yeah, okay, so this is the battery cover. And then here we can see a typical lithium-ion battery and electronic device. The reason you use lithium-ion is because charge density is really good, so you can store a lot of energy in a small package. The downside is basically it's really hard to maintain. Like if a normal car battery you overcharge, it's not too big of a deal, and if you don't charge, it's not too big a deal.
Deals with lithium-ion.
So we really have to make sure that you don't overcharge or undercharge. So typically, there's some added cost there with circuitry to make sure that the battery's properly maintained. But that's pretty cool. What's really interesting though is basically this battery.
Yeah, I'm trying to see if, because there's some people listening on it, and I think Xuehai talked about solar. What are you doing?
I think it's, there's nobody that can hear me from over there.
To the phone. No, you need to talk to the
Put the
phone.
microphone.
No, the phone is wait.
They don't hear the phone over the
phone.
screencast.
And turn the speakers off.
Oh, can they hear over the screencast?
What?
Can they hear over the screencast?
They can hear Jeff, but I think you're talking a bit quieter. So.
Okay, I will try to talk very loudly for the people on the other side. Yeah, basically. Okay, so what's really interesting here is that because of space constraints, they have to put a battery on the opposite side of the circuit board, and you have to run this really long wire across. If this thing consumed a lot of current, that would be not the greatest thing to do. Basically, you wouldn't be able to get the most charge out of the battery because as the current goes through, you lose voltage, and it's just kind of like a compromise they have to make. Oh, okay, so that should be enough time. Right, so these are all injection mold parts. 1, 2. This is also compression molds. Also compression mold. And I'll talk about that after. And this is stamping. So where you go, or you go? No, you can go. Okay. Yeah. So these are injection molded parts, and I had a slide up there that's pretty similar, but the difference between injection molding and compression molding is that compression molding comes in and pushes the part between the mold. Injection molding actually shoots the plastic into the mold. It's like a soup, everybody uses it.
It's basically one of the most micro things that we use in plastics manufacturing. It's super fun, and it's very similar to this. It's just imagine that instead of compressing this, you'll still have your cavity, you'll still have your core, but you'll be shooting molten plastic at very high speed to fill up this entire space.
So on an injection molding part, we'll be looking for things similar. We'll be looking for that's the line that we talked about earlier. So any two molds that come together, you can have that part. We're going to be looking for injector pin marks, and we're also going to be looking for gating marks and any defects. So so defects is a byproduct of bad design, and we'll kind of get into that later. But in the case of this piece, you can actually see the gate mark. It's actually right there on the piece. Sorry, there on the piece. And you can see because they kind of tried to wipe it out afterwards. But there's clear evidence, and it kind of gives you an idea of how the part was formed and how the plastic flowed. There's other things to think about, I guess, when designing pieces like these.
What does the gate do?
The gate is literally where the plastic comes in from, into the mold. So that's it's literally same like any gate. And the molds are not just one part; they're hundreds of parts. Right? Yeah, so it depends. So you can have multi-cavity molds. It depends on how big or small your part is, and the cooling that you need for cooling channels depends on anyways. So you can have a multi-cavity tool. So what does that mean? So multi-cavity tool literally means you have hundreds of support, thousands of parts, not thousands, hundreds of parts on it. Yeah. It just depends on the size of your whatever molding. In this case, it's probably not. Anyways, so we also look at part design.
there's kind of rules when you're designing for plastic that we look and see if they broke them, and if they broke them, how. So in this case, this is a pretty simple part. They did, so if you see here, it's really hard to see. So by the way, this is like kind of shiny plastic. The shinier it is, the easier it is to see defects, so avoid that.
I can barely see that, just like.
You can see it on the
camera. Oh, you can.
So,
Yeah, I can't see because but anyways, this is what we call sink right here, and sink is a byproduct of having a thick section in, I guess, yeah, a locally thick section if, you know, the area around is thin. And essentially it's an issue with like the cooling of plastic, and you'll see it on the opposite side. I can show more examples later. Yeah. But that's bad design. They obeyed it here when they did these ribs. So ribs are these features that give this part a bit of rigidity. If you'd imagine if this part was totally flat, you would be able to bend it a lot easier. So it's kind of hard to express, but imagine like, you know, this. No, they actually did a good job of doing it. But in any case, ribs are for structural rigidity. And, so it's talking about injector pins. So you have your piece and you molded it. Now it's on the cavity side, side.
Hold it like this.
Yeah. So anyways, it's stuck on the tool.
Doesn't matter.
Because it actually, what happens is you'll shoot it, it's really hot, and then it'll kind of compress or shrink as it cools down, and it'll be stuck to the tool. So what they do is they actually kick it off with pins. So you can see it all over this part actually. There's 1, there's 2, 3, 4, 5, 6, blah blah blah. So yeah. So this is kind of an interesting.
They did a good job.
This is like, I won't check about the draft. We will check about the draft.
Yeah.
Okay, you go.
Usually on like cups, cheap cups, you'll see injector pin mark usually right at the bottom, right over here. Also, a cool thing about plastics is if you have really large plastic parts, you'll have multiple gates to make sure that you can evenly come in and spread the plastic.
Right.
So yeah, there's basically one circuit board on this whole thing. This is it. So because it's a speaker, I think there's basically 3 components. There's the power management for the battery, and then the audio codec, an amplifier for the actual speakers here. We can go straight down on this. So I didn't actually spend the time to like figure out which is which, but it's one of these black things. What's interesting here though is, I think, so 2 things on this side. This board you see is soldered onto the main board, and that third component is the Bluetooth chip, because it's a Bluetooth speaker. Yeah, it's right here. So typically you do this because engineering RF things is actually kind of difficult and requires a lot of effort and integration on your board. So if you want to spend a $20 speaker, you basically everything else just wire together, it should work, and you buy this Bluetooth chip and just solder it on your board. So you can see the antenna is right here, and then the rest of this is soldered on. Another cool interesting thing they did was they put this like red goo all over the connectors. I think that could be 2 things. One is for reliability, just to make sure that the connector doesn't rock out because it's a portable speaker. Yeah, so you'll see on this right here. There's like red stuff. Yeah, and then the other thing is that the factory you can also just check that things haven't disconnected while you're assembling. Yeah. So what's really interesting is I think less so on this side, but if you look on the other side, a lot of these capacitors are like soldered poorly. So if you look at, so I'll get everyone to see that. Just pull back. Yeah, so these 2 caps should be like parallel to each other, and I'll just reach a bit further.
Okay, you gotta come back a bit because it's not gonna focus on that.
Okay, there you go. These just hold it. So these 2 caps are kind of like touching each other on this side, but not on the other side. And what normally happens there is like you get too much solder, the component will float as you send it through. Basically, like reflow is you put all the solder on, and then you send it through a machine, and it ovens everything, and it all falls into place. So yeah, you can see a lot of that happening. If you like make a ton of units like this, one will fly off, or it'll connect to something that it shouldn't. Maybe it'll short, and your board is toast. Another thing that's interesting though is typically in PCB manufacturing, you put things called test points. So you see these like little circular things. What happens is like a fixture comes down with like some needles that you can control what signal you put in. And you do this when you make the board and you assemble it all together, you have put it in this fixture and it basically tries to exercise all the features of the board. So it's like, oh, I'm gonna press all the buttons, I'm gonna make sure the Bluetooth communications work. And that way you exercise all the features and you know the board works before you plug it in. The reason you do this is you basically test everything before you plug it in, and then everything you put in should work, so that you don't like spend, I don't know, like half a day through the whole line making this part, and then at the end you realize the program to take it apart again, or if it doesn't come apart, you just throw it in your trash. So the earlier you find out there's an issue, the better.
What's the typical failure rate? Are these errors happen that would make you lose board? Would they happen at 1% of the time?
So that all depends on how early off you test and what your process is. Yeah. So if it's like a brand new process and it's a brand new product, depending on how much in a rush you're trying to release it, you could have like 70% yield, so like 30% units are duds. The thing is, it's like 30% out as opposed to if you just like put everything together. The more complex the system, if 1% fails, but it requires 100% to use, you'll have no yield, right? So yeah, basically it's kind of like that. It's really how well your processor is at each point and how it all comes together. So there's also this notion of like IQC and OQC. So basically, IQC is incoming quality control, OQC is outgoing quality control. So basically everything you get in, you test as the other whoever made it comes in. That way you know it all works. Yeah. Okay, but I just want to make one final note. Is what's really interesting is this thing has a microphone in the middle of this board, and this thing does not have any microphone features. Yeah. I don't know why. No, it's really awkward. Yeah. I tell you. I don't know if they try to like put voice control in here, but if you look at the board, there's like basically no chips that could do that. Maybe you could do like Bluetooth calling, but I don't think that actually ever worked. Maybe that was the intent, but it's on there. I don't think they ever tested it. Yeah, so that's basically the board. Pretty cheap. Yeah, exactly. Yeah.
How much of the cost would the board be?
Not cheap. It really depends, but something like that. So when you buy a module like this, it's actually more expensive. But then you don't have to put engineering over it. So a lot of like Kickstarters and stuff, when you like open it up, a lot of RF modules will be like modules. I think there was this. Yeah, I don't remember the exact product, but basically you open it up and it's like basically the equivalent of like they put like a Beagle bone and then like an RF module and just connected them together on the same board, and it had a giant LED on. But it's a pretty nice product.
Yeah, RF is notoriously hard to design for, especially with Mac, because any metal you put near RF, so that your antenna, is bad for it. Like you have to, they always want more space. Like move your metal away, and like you can never fit everything in. So.
And if your company's really anal, then they like say move the plastic away. You want to know what kind of material the plastic is made out of, how much plastic it is, how far it's going to be, and like they do like a full like thing of like, hey, how much is this like big thing of plastic is going to affect our performance? And even if it's something on the order of like 0.05%, they want to know about it so they can factor it in.
So if you want a number, it's like $6 or $7 for that board,
including
just the whole thing. Because this module would be like $5, and the rest would be like super cheap. Yeah.
All right, so there's other ones. Okay, so we can go over these, but these were the speaker grills. We kind of went over. I don't even know what they went over anymore.
Here's an example here.
Oh, there you go. This was okay. So this is kind of like the main enclosure, body, whatever. They have the two drivers here, so you guys kind of recognize this. You've seen it on your speakers. This is what actually makes the sound, whatever. Right, actually back and forth. And in this case, they're actually venting the sound through these sections. This is, I guess, what you call a speaker grill. It's essentially this large, like, metal sheet, and the holes are all stamped. So, you guys know what stamping is? It's like, if you stamp a stamp, you literally go like this, right? That's stamping. In the case of holes, you literally have like little, like, pins that come through and just stamp the piece and like punch out that specific section.
Can you zoom in on it?
Sure. I guess
How do you make sure that like when you stand it, you can just like destroy these?
Yeah, you can like so you're supporting it from the other side. You're making sure the piece isn't too thin. You're making sure in this case the holes aren't too close together. You can imagine like sushi. Yeah, and if it's like really a problem, you can go with other processes like Kemench, which literally like just eats away specifically at material in like a local section. So you can say, oh, I only want these holes, and they'll be able to like mask it and take acid essentially and eat away at that specific section. So there's less forces on the section. Yeah, but it's a pretty expensive process. These parts are really simple. Like they stamp the holes and then they stamp the piece into the shape. It's like U shape, and you can tell because well, we're looking for things like this, but you can tell because the holes along the curvature are actually slightly oblong. Like they're not circular anymore. So we know the holes were formed first before they actually stamped it into the shape, and then they paint this thing. Yeah.
I think the process you talked about, a good example would be, I don't know if you guys remember the old MacBooks, where you couldn't see the lights, but when you press the button, you can see the light shine through. That's the kind of process where you make really, really tiny holes through a piece of metal, and you use something like that as a process where you wouldn't be able to see the LEDs when they're not red, but like shines through.
Yeah, actually, this thing had LEDs, as far as we know.
Right here, yeah. So,
which is like a really big feature in consumer electronics. And a lot of people do it poorly. And a lot of times the reason why they do it poorly is, you guys may or may not know this, but it's the uniformity. So the more diffuse and like even you can get it, the better. And the challenge is that you have these like discrete packages on your board. So these are really tiny. So here's one. You guys can see.
Are those like a 402 or a 201?
Oh yeah. Spin that wheel.
You spin the wheel on that.
So they did a pretty good job at evening it out, but you can still see if your eyes are. Yeah, I can actually tell.
Yeah,
it's bad. But you can usually tell where the discrete LEDs are.
Different colors. Yeah.
So a good company will be able to make this rating entirely uniform, even though the light source is here. So, like blending it together is actually a very difficult task, and you blend it together by doing light pipes. So light pipes is a really big feature. It's essentially this like clear plastic that you guys see here, and what it does is it diffuses and spreads the light out evenly. And yeah, that's the job. I mean, you can see it right here as well. So we would take that apart and look how they shoot the light in, and the geometry and things like that. Other notable pieces, or we can talk about the entire thing itself. So this is the main enclosure. Whenever you're doing speakers, you need like a back volume, which is essentially the entire body of this thing. They have a passive radiator in this case. Kind of technical, but essentially this allows you to have better bass. It kind of tunes your frequency like curve, so you can have more bass, as opposed to like if this was a straight wall and sealed off. I guess other notable things, this piece. So typically, a really basic mechanical concept is undercuts. So I don't know if you guys can see this, but this feature is what we call an undercut. So from a molding standpoint, if you guys can imagine, if the two molds close like this and it pulled upwards, you wouldn't be able to create this feature because this hook would get in the way. So let's say I'm the other half of the mold and I'm trying to pull up now. I can't because I'll nick this and catch on and just break it. So if you want that feature, what can you do? They cheated, or were cost conscious, and actually did what we call a pass-through. They actually had the luxury of coming through from the backside and on this bottom half of the mold, putting essentially a standoff that can create this feature, so that when they separated the mold, they could just go like this. Other things you can do if you're a little more advanced or less cost conscious is lifters and sliders. There's like an image in the presentation, but it doesn't really matter. Essentially, as the mold opens, what happens is, due to the geometry of surrounding features, it'll cause the hook, or whatever you want to call it, the feature that creates the hook. So say this is the hook that we were talking about earlier. What happens is, this piece will move outwards and up as the mold opens. It's kind of hard to explain. We can watch the video. Other things, this thing is pretty well sealed, as any speaker should be. From a 3D standpoint, it'd be kind of nice to actually just print it as one seamless piece, so you don't have to worry about like these parts not fitting together well and not sealing. They took all the slop away from with just like gasketing, which is essentially like the sponge material, and that's how they kind of seal the entire thing. So. And then we look at like how they manufacture this. All right, I think that's it. Cool.
I just want to know, what was the circular deformations on the piece? Like, what was it from again?
Which one?
Like,
There's
like those surface, the circular.
Oh yeah, take it. You guys can play with these. These are called ejector pins. So
the flat.
yeah, ejector pin like marks.
Oh,
So
okay.
literally, like, so you can imagine, like we have mold around this like this, right? And then we move this section away. And right now, this piece is stuck on this piece. Okay.
Yeah.
This is the other mold.
I think it's on the side of the gate.
It depends if they do a hot runner.
Yeah.
Technically, it doesn't have to be. Anyways.
Yeah.
So it's stuck on this side, and it's pooling, so it's shrunk like this, so it's hard to get off.
Yeah.
So they have these pins that literally come up through the mold and kick it off.
Oh, okay.
Yeah, so that's what that is. All over. Got it.
Well, it's not like completely cool.
You don't wait until it's completely cool because the time you have to wait for it to completely cool is like it's pretty long. So they just kick it off early, just keep pumping parts out. Like injection molding, like the rates are like hundreds per hour easily.
Could we use pressurized anti-stuff pins?
Yes, but it is not as easy, I would say. And now if you have like a pressure imbalance, your pieces are going to go like this, and like fly up weird. Like it's nice to have like a physical thing to really like make sure you're even every single time.
Is this what you guys do for a living?
Yes.
I know about tooling, but I generally work on product assembly. So like I do more like line stuff. So like you know how you work with electronics. I basically we get all these things, and like if your company's really anal, everything's supposed to fit in really really tightly. So we're the ones who figure out how to assemble things. And what I do is like sometimes like these guys just took it apart kind of thing, right? But what I would end up doing is we'd be saying this thing needs to fit in this with like an accuracy of like 50 microns. And obviously no one's gonna be able to do that manually. So you get cameras and machines, and you just put the parts in a machine and let the machine figure out how to do it. So like I'll work on machines that kind of figure out how to like do complex assemblies versus more like there's tooling, which is I think more difficult.
Yeah, I think it's basically any part you see here, there's another thing that is built to put it together.
Yeah.
Well, how do you
What's
test that?
your job title?
I'm kind of product design, so if I were doing this, like, they would say design speaker, and I would design this.
So I think
like
typically
all the mechanical ones.
for hardware in the valley, it's like there's ID that makes the design, like the shape of the outside, and then there's PD, which I think people get confused, but yeah, PD does what's basically everything inside, and then how it all fits together.
Yeah.
And then basically they go, hey, you get this rectangle, and then the electrical engineers try to fit everything in the rectangle.
It's no joke, like it's like a push and pull process.
And then they go to the manufacturing guys, and be like, okay, this is how it's gonna come together. Figure out how to make 2 million of these in like a couple of months.
And we all work together.
And then we all work together.
We kind of shit on each other.
Yeah.
It's like, so he's right. IG defines the exterior shape, and then we make sure, as PD, everything fits inside, and also like some of the interactions. So we would be sourcing like these buttons and like making sure they feel good every single time you press them, which is like the time. And we make sure, because there's mechanical components underneath that are actually like, helping with this interaction. Like we make sure that it stays up to par after X million cycles.
Yeah.
I use industrial design.
That's right, industrial design. Yeah.
I have another question.
Yeah.
So when you're doing injection molding, how do you make sure, do you have to do anything after you've made one product before you can start putting the other thing in? Like, is there residue, like plastic residue? And stuff like
So that's like so that's like kind of a machine question. You do have to what you call purge a machine. It's actually the same for 3D printers.
Yeah.
So like you'll shoot a material and then you'll have to actually clean it out. So you can have cleaning solution. You can in the case of injection molding, they can just throw in like shitty resin plus like some cleaner stuff, and it'll just kind of purge the system.
And do you do that every time or like?
Yeah, every time. If you change your resin, you have to. If you're using the same resin, you can just keep throwing that stuff in.
So like every time you want to change a filament in your 3D printer, you would take it out, clean up your extruder, do all that. But as long as you're feeding the same material, usually unless you maybe if you leave it like for a while, you'll have to clean it again. But
So you mentioned before like removing seams and stuff, and someone showed me like the MacBook charger, like the newer MacBook charger. Like it doesn't have any seams on it. Like, I'm not sure how exactly you do that. Especially when there's stuff inside of it.
Okay, so
there's some scratches on the outside.
My guess is so this is a little more complex. So they probably did ultrasonic welding.
something like that.
Yeah. So if you can imagine this L piece,
I don't think I'll just once.
They probably have this L piece that comes out, and all the boards and stuff go in first, and they seal everything off with this L piece, and then like a laser or could be laser or could be fine. I don't know. Whatever. Essentially, something comes down and welds these two surfaces together. So what that means is essentially it imparts enough energy that the two surfaces melt and then form a bond.
And then you post-process it.
Yeah, and you make that. So you have to clean the seam. And this could be like a precedent over, be a threaded connection, like it's kind of a weird piece, but yeah.
These are expensive as well to make. Like there's one thing that you guys notice, like there's a lot of like tiny small Apple products that are super expensive. And a lot of people think that Apple makes a ton of profit off these, but because they try and pay as much attention to detail they would to like a small accessory part as they would to like an entire product, those small things actually cost a lot because we tend to employ like really advanced manufacturing techniques.
Also, you can buff out the split line that we talked about earlier. You can buff it out and then plastic, and then polish it after, like plain polish or like vapor polish. So I'm actually seeing the seam a little bit, so something fucked up. But this is really well done. Yeah.
Wait, so where is the seam?
In this case, it looks like it's actually on this side. It did a really good job. So you can cheat by hiding it on curves, and like a curved surface is a little harder to see than on like a pure flat surface. Like you can imagine you see like a big flat plane, like any bumps or anything, it's easy to see. But if you hide it on a curve, this is going to be really hard to see.
Probably see it.
Or something. So it's going to be impossible to see. I can point it out to you afterwards.
We just have
I know the previous version of this had the seam right down the center of the.
Yeah, so that was like a clamshell design where like they did the two parts and they just go. Yeah. Any other questions?
Listening, you guys can go up so.
How much of the executive?
There's a lot of scratching on the outside.
It's been overkill though. Cool. Thank you guys very much.